Hello, glad you're here. We're going to talk about section 6.2 today. And section 6.2 is all about exponential function modeling and graphs. And so it's just a deeper dive into talking about exponential functions a little bit more. And since we're still talking about exponential functions, we have Little Women with us. Whenever we see them, we remember that we're talking about exponential functions. This will be the last section on exponential functions. I think this picture is when Beth gets married. That's kind of a high point of the movie. Okay, so remember that an exponential function has the basic form like this. And what's important here is a and b are going to be some constants. X is a variable. It's your input variable. So this is a distinguishing feature of exponential functions, is that your variable isn't down here somewhere. It's up high in the exponent. So I want to ask the question, what if x equals 0? And think about this graphically. So in our graph, here's our input axis. Usually this is x. And our output axis, usually this is f of x or y. Okay, let's think about if x is 0. Then we have f of 0 equals a times b to the 0. All right, so that tells us that f of 0 is a times b to the 0. Whatever this number is, any number raised to the 0 power is 1. So f of 0 is a. This makes sense because a is our initial value. We always talked about that. But here we see algebraically why that's true, that when your input is 0, which means we're not here, we're not here, we're not here on the x-axis, we're right here at 0, then our output for the function is a. And so this is what it graphically looks like for a to be the initial value. Okay, and then we always talk about b is a number that is called the change factor. And if b is greater than 1, then we get an exponential function that grows. If b is between 0 and 1, we get an exponential function that decays, that gets smaller. And we never talk about negative b in this section. Okay, let's look at an example. Oh, before we do that, so for this, pretend that our b was greater than 1. Our function would look, it would grow exponentially like that. But the function is always going to hit the vertical axis at a because of all of this right here. Okay, for our example, without a calculator, or Desmos, let's see if we can think of what the following would look like. So say that I give you the function f of x equals 2500 times 1.1 to the x. This is definitely a standard exponential function. We have our a initial value, our growth factor raised to the x power. Okay, so this right here being our initial value tells us that the function is going to hit the vertical axis at 2,500. And the fact that this growth factor is greater than 1 means that in general, it's going to grow like this. Not super fast because it's going to go down that way. It won't grow super fast because 1.1 is fairly close to the number 1, which would just be a flat curve. Okay, let's try another one though. Let's say that g of x equals 4,000, 0.8 to the x. And so we graph this without any kind of calculator. This is our initial value, 4,000, so that's where it hits the vertical axis. This time our change factor is 0.8. This is between 0 and 1. So we know in general that this function is actually decaying exponentially. So this is what g of x would look like. And this is what f of x looks like. Okay, last thing I want us to find f of 2. And we'll find g of 2. Okay, this just means that we're going to put 2 in for the input value. So this will be 2,500 times 1.1 squared. And this part I do need a calculator. 1.1 squared times 2,500 gives us 3,025. So when our input value is 2, then the point on the graph is 2,3025, and that makes sense because it has been climbing. Let's try this one. G of 2 is going to be 4,000, 0.8 squared. 0.8 squared times 4,000 is 2,560. So on this graph, we're going to see the point 2,2560. Here's 2. And it has gone down probably a little more dramatically than what I've drawn here. But so graphically, everything looks like what we think it should look like. This one is growing, this one is shrinking, it's hitting at the right initial value. For the rest of this video, we're just going to look at 3 examples. And our first example is right here. According to the World Health Organization, the population of China was 1,323,345,000 people in 2005. So that means 1.3 billion when you tack on this thousand. Between 1995 and 2004, the population grew at an average rate of 0.7% annually. As soon as we see this, we know that we're probably going to be talking about an exponential function, because when things grow or decay at a certain percentage rate, that is indicative of an exponential function. Assuming the population will continue to grow at this percentage rate, model the population of China as a function of years since 2005. What is the projected population of China in 2011? Okay, so we have 2 jobs. We have to come up with a model. That means just find the function that describes this situation. And then this question here, what is the projected population of China in 2011? So we'll start by trying to find a model. And I like to think about what my inputs and outputs are. Model the population of China as a function of years since 2005. So on our horizontal axis we have time, and our vertical axis we have population, and it's growing, and so it'll look something like this. And then I always like to get my data in a table. So my input is T years, population of China, and let's see what we know. Okay, in 2005, this was the population. So population is going to be in thousands. So in 2005, that's when it's year 0, because they want us to use the function as years since 2005. In year 0, this was the population. 1, 3, 2, 3, 3, 4, 5,000. And that's all the data they've given us. They've told us how it grows annually. And later they do want us to find what is the projected population of China in 2011. That will be 6 years after 2005. So we're going to be looking for the population 6 years later. All right, we totally can do this. We know that we want basically something that looks like y equals a b to the x. This is what an exponential function model looks like. But in our case, it's going to be p as a function of t equals a times b to the t. Now, first question is, do we know the initial value? Yep, it's sitting right here. So this equals a. I know it's the initial value because it's when t equals 0. Second question is, do we know the growth factor? No, but we know something related to it. This is not b, but this is the percentage rate of change. So I know that r equals, and I can't put 0.7 because I'm going to take it into an equation. I have to use the decimal representation, 0.007. This is what r is. And so I know that b always equals 1 plus r, so b equals 1 plus 0.007, so b is 1.007. Good, I have my a, I have my b, and so I have everything I need for the model. So p of t is going to be 1, 3, 2, 3, 3, 4, 5 times, and b is right here, 1.007 raised to the t power. This will give the population of China in thousands as a function of years since 2005. So I've done the first thing they asked me to do. I came up with the model. Good. The next thing they asked me to do is find what p of the population in 2011 will be p of 6. And I'll just use my calculator for this. Times 1, 3, 2, 3, 3, 4, 5. And we'll just round to the nearest whole number since we're talking about population. Okay, but I'm not done for sure, because then I have to tag on that in 2011, the model predicts this many thousand predicts that many people in China. Good. Our second example deals with atmospheric pressure as a function of elevation. At 0 meters elevation, atmospheric pressure is 14.696 pounds per square inch. At 8,500 meters, atmospheric pressure is 4.801 pounds per square inch. As elevation increases, atmospheric pressure decreases less rapidly. Okay. Use an exponential function to model atmospheric pressure as a function of elevation. Then use the model to predict what the atmospheric pressure at 6,000 meters would be. Okay, so first I want to look kind of graphically what are on each axis. Use to model atmospheric pressure. So let's do P for pressure as a function of elevation. Okay, and so this indicates that we're going to use an exponential function, but things are decreasing. So in general, this function is kind of looking like this. And let's get whatever we can into a table. So elevation and atmospheric pressure. At 0 meters elevation, the atmospheric pressure is 14.696 pounds per square inch. At 8,500 meters, the atmospheric pressure is 4.801 pounds per square inch. Okay, this is enough. And knowing that we want to use an exponential function, we have our 2 data points. And nicely, we have the initial value. So our model is going to be atmospheric pressure as a function of elevation equals some initial value times the change factor raised to, oh, this is not actually, I don't like the variable e because that's a real number. So we'll do h for height. The elevation or height. So we'll call elevation h, our variable h. This looks terrible. Okay, let's start this all over. The pressure as a function of height is a times b to the h. Okay, I feel better about that. Okay, this is awesome because this is our a right here. And because it's our initial value, we just need to go figure out what b is. And we have 2 data points. They're not really consecutive. So to get from this data point to this data point, we've been doing a series of multiplication by some change factor, and we need to discover what that is. We're going to use the formula b equals y2 over y1 raised to the 1 over x2 minus x1. Formula always allows us to find the change factor from any 2 data points. Okay, so b equals 4.801 over 14.696 raised to the 1 over 8,500 minus 0. 4.801 divided by 14.696 raised to the 1 divided by, remember all your parentheses, 8,500 minus 0 is just 8,500. Okay, when I push enter, I really hope I get a number that is smaller than 1, that's between 0 and 1, because I know that this function is decreasing. Oh, good. Whoa, it's pretty close to 1, but it is smaller than 1. So we find out that b equals 0.999868. I'm going to keep all those decimal points because it's so close to 1 that I need to find out where it's different than 1. Okay, we have a, we have b, we have everything we need for our function. P of h equals 14.696 times this guy, 0.999868 raised to the h. This is the formula that will give us atmospheric pressure as a function of elevation, or the height of an object above the Earth's surface. Last question is predict what the atmospheric pressure at 6,000 meters would be. This is our elevation. This is our h. So we're going to predict P of 6,000. I'm just going to put a 6,000 in for this right here. 0.999868 raised to the 6,000 times 14.696. This will be a number between these two numbers because the atmospheric pressure at 0 is this and at 8,500 is this. So it's going down, but it needs to be greater than what happens at 8,500. And it is. It's 6.5. Yeah. 6.656 pounds per square inch is the atmospheric pressure at 6,000 predicted. This is the last page for talking about exponential functions. So we have the last, this is the last that we're going to see of Little Women. 6.2 continued. after this, we're going to start talking about logarithms. But this today, we're going to talk about exponential functions. If you want some extra credit, turn in number 38 on page 353 to me. Just message it to me in Canvas, and I'll give you 2 extra credit exam points. All right, we're talking about regression for the first time in an exponential context. This works just the same as other regressions we've seen. We've seen linear, we've seen quadratic, probably we did some cubic regression. I can't remember if we had time to do power regression. These are all types of regressions we've seen, or at least linear and quadratic we've seen. And now, sometimes your data will look, you can kind of tell that it's growing real rapidly, or they will tell you to do an exponential regression. So we need to get at least a little practice with exponential regression. It works in a very similar way, though. For this problem, we have a set of data that relates years since 1980 to the NBA average salary. So in year 0, in 1980, the average NBA salary was $170,000. 5 years later, in 1985, it was $325,000, and then it keeps going up and up. So we want to find a regression model, an exponential regression model for this data, and then we'll answer this question: does the model predict that the average MBA salary would be more or less than $3 million in 2010? You can do this regression on a TI calculator or Desmos. I'll show Desmos first, and then I'll show the TI calculator. So on Desmos, we put all this data into a table, and then the regression that you're going to use is this, excuse me, y1 tilde AB x1. Just like normal, we're using x1 and y1. Importantly here, this log mode box has to be checked. That way your answers will match the answers in WebAssign. If you don't check it, your answers will be off. It's just a different way of doing regression. By default, Desmos does it a different way, but we want it to do the regression excuse me, in log mode. Okay, once we do all that input, of course, Desmos just kicks it out. And Desmos tells us that, they're using B here, so the average salary as a function of years is 161.43, and then our change factor is 1.16919 to the t. Regression's awesome because your calculator or Desmos really does the work for you. So it's fitting this curve. And when I plugged it into Desmos, this is what it looked like. These green dots were the actual data, and this is the exponential curve that this data follows. So yeah, that's really climbing quickly. I mean, 20 years after 1980, just think of how quickly things are going to grow after that, according to the model. Is that realistic? I don't know. There's probably a number of limiting factors. Okay, on your TI, you're going to go to stat mode and enter your data. Let's see, we've got 0, 5, 10, 15, 16, 17, 18. And 170, 325, 750, 1900, 2000, 2200. Of course, always make sure that you've input all the data correctly. We'll quit that and get back to stat calc. And then we look for exponential regression, which is right here, number 0. Okay. And it gives us the same numbers. A is 161.43 rounded, and our change factor is 1.16919 rounded. And then the last question to answer is, does the model predict what does it predict in 2010? So we're looking for B of, let's see, 2010 would be 30 years after that. So that's going to be 161.43 times 1.16919 raised to the 30. And the number I get from that is 1.16919 times 161.43. And this tells me that in 2010, 17,560,000, 1, 2, 3. This is the predicted salary in 2010 for an average NBA player. I don't know if that's true. I doubt that that's true. I think that the model, like I say, it can't go exponential forever. For this data, it fit it pretty well. But as you're getting out and out, the model kind of breaks down. So that's a good lesson that the models, you kind of have to keep tweaking them with more and more data that you get. All right, you've got everything you need for 6.2.